Hello everyone, welcome back to lesson number 29 for BC Calculus, where we're talking about area between two curves. Example number 7 is asking us to integrate or show the region visually by the integration of 0 to 1 of the square root of x minus x squared dx. Now, I'm going to be honest with you guys, I'm going to be very just sloppy with this because if you were to graph it to scale here, this area would be so small. So 0, and I'm just going to pretend like that every 3 is a 1. All right, so every 3 is 1. So then I'm going to go ahead and just do this. So the square root of x is going to look something like this, where this is 1 and this is also 1, because it's easier to see it that way. So that's what the square root of x looks like. This is also letting me know that this is the top function of the region that I'm looking for. And then I want to look at the bottom part of this. Well, this is going to be the x squared. Remember, the negative that's in the equation is always the subtraction, right? It's f of x minus g of x. So I want to graph y squared next. It's going to look something like this. And even to this scale, even though I made the scale like this, our actual region that we want to find is from 0 to 1. So it's just going to be this region right here. So even though I blew it up a little bit, you could imagine if I just left it and this is 1 here. So it's really hard to do it that way. So that's what we want. It's not something you're going to ever have to draw, but it's just always a good indication of what we need to do with it. So let's look at example number 9 and put it back on the screen here. It says a vertical line, x equals b, divides the region between y equals 10 minus 2x and the x and y axis into two equal areas. Find the value of b. So the first thing we're going to do is we're going to just kind of visually look at what's going on here. We know that we have a y-intercept at 10, right? When x equals 0. When x equals 0, then y is going to be 10. When y equals 0, we're going to get that x is going to be equal to 5. And so we have this line. Or we could just, go down 2, right 1, down 2, right 1, blah, 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 to get this. So the region that we're looking at is going to be right here. So we want the area that's bounded by the line y equals 10 minus 2x, the y-axis and the x-axis. And we want to find some value of b, x equals b, where the area to the left is going to be equal to the area to the right. Now, clearly, common sense says I cannot do it at 2.5 because this would be so much greater than this. So I need to be closer to this side. So I'm going to be less than 2.5 is what we're going to do. So let's solve the problem. Well, let's look at it this way. So from 0 to b of our function, 10 minus 2x dx, we want that to equal from b to 5. That simple, ladies and gentlemen. We're starting at 0, and we're going to b. This is always our top function. This is always our bottom function, right? So it's going to be 10 minus 2x, technically minus 0, because this line is y equals 0, but we don't need to do that here. Dx is equal to b to the 5 dx of 10 minus 2x dx. So when we integrate this problem, the beautiful thing is that this becomes really, really easy to integrate. Okay, so now we're going to plug in b. We're going to get 10b minus b squared, minus 0, but the zeros are obviously going to cancel out here. And then we're going to go and get 50. So it's going to be 50 minus 25. That's our f of b part, or f of, so really it's our f of 5 part. And then we're going to go ahead and plug in, just like we did before, and get 10b minus b squared. So when we simplify this, we're going to get 10b minus b squared is equal to 25 minus 10b plus b squared. And the good thing about this, ladies and gentlemen, is we move the b squared over, we're going to get 2b squared. We're going to move this 10b over, we're going to get negative 20b plus 25. And what kind of sucks about this problem is the fact that we can't full out of 2. So we could do one of two things. We could use the quadratic formula, or we could just graph it. And I think we would just graph it here because I don't want to waste too much more time on this. But if you were to find the answer, you would get that b is equal to approximately 1.464. So if I give you guys a question like this, it would be something that's easily factorable so you guys can find the values of this. But at 1.464, you get that answer. All right, so let's go on to some strategies now of how to do some of these questions. And let's move on. Okay, so as you guys see right here, we're going to ask to find the area of the regions bounded by f of x equals this quadratic, and then g of x equals this quadratic. So one of the things that I want to stress with you guys is simply knowing that you can find, this graph. The idea of this graph is by, first of all, factoring it. So again, I'm going to use the calculator, but I'm not going to use the calculator. You'll see why. So for this particular example, we know that at x equals 3 and at x equals 1, we have intercepts. So at x equals 1, x equals 3. We're also going to take into account, if you guys notice, that we have a y-intercept at y equals 3. This and the fact that it's a quadratic. It's a quadratic and it's positive, so I'm going to know it's going to look something like this. And yes, I can find the vertex if I want to, but again, rough sketch is all we need for this. So we know the graph looks like this. I can also then, for this one, pull out a negative, and I'm left with x squared minus 2x minus 3. And then I can go ahead and set that equal to 0. And I can go ahead and factor this out. 3, 1, and then I can do negative here plus here. So I get x equals negative 1 and x equals 3. We'll go ahead and do negative 1 and x equals 3. That's awesome. And we also know that this intersects also at the y equals 3. So we have a graph that looks like this. Now we're going to find the area of this region. So when we do the problem, guys, we're going to integrate from, their intersection points. So their intersection point is at x equals 0, and the other intersection points at x equals 3. So x equals 0 and x equals 3. My top curve is going to be purple, so it's going to be negative x squared minus plus 2x plus 3 minus our f of x. Now I want to show you and tell you a couple things about this. You don't have to necessarily write this out like this if you want to. What you could absolutely do, and I encourage you to do it, is just go ahead and, since I've given you that g of x is this, just write g of x here minus f of x. If I see this, I know that you're telling me that this function, just g of x, is the higher curve. So now you have to tell me what g of x and f of x is, or the problem has to state it for you. So this is a completely legit setup, and honestly a preferred setup than what you see right here, because this takes a lot of time to write this out, and then you don't have to worry about minus parentheses all this stuff right here. So that's what I like about this problem. Now let me also show you guys the calculator part of this. So what I have done for you is I went ahead and typed in my calculator the functions that you see right here. And let me actually do detach my little thing for this. So then what I want to do is I'm going to get out of this. Oh, and I do want to make sure that I remember, as I do this, that my y sub 1 is f of x, and that my y sub 2 is my g of x. And I usually like to do it alphabetical, so f then g is kind of how I always think about it. So then if I go to Math 9, I can integrate from 0 to 3 on my calculator. And instead of typing this whole long thing out, this whole thing right here, I can now say that g of x, which I can get to very easily by alpha trace, is y2 minus our f of x, which we identify as y sub 1, dx. And so let the calculator do the problem for us. And so that's a beautiful thing to do. And the reason why I'm strongly suggesting this is that as you guys do area, you may have to find the volume of these things, you may have to find the shell of these things, and so it's just nice to have them already in there for us. So then we look at our answer. This answer is going to be equal to, or this area is going to be equal to 9. Okay, so like I said, just a nice little strategy for you guys to be able to do that. I think that's it. I think that's all I need to show you guys. The rest of these examples you guys can practice on, but that's the idea of what I wanted to get through. And yeah, so I hope that's helpful. Remember, as just a quick summary, ladies and gentlemen, so I want to try to do this for all of my Unit 6 information things here. So a quick summary. Area between two curves. So when you're finding the area between two curves, because when we do volume, it's going to be slightly different. The cross sections, even more slightly different, and shells, a little slightly different. So let's go ahead and do two curves. And we can say that they intersect at A and B, and this top function is f of x, and this bottom function is g of x. So it's very clear. Then the area of this shaded region is going to be from A to B of f of x minus g of x dx. Pretty straightforward. Then if I do something like this, and it could be like, let's, have a little fun with it. So something like that now. Then this is going to be D. This is going to be C. This is going to be f of y, and this is going to be g of y. The area of the shaded region is going to be from bottom to top, C to D, of our right function minus our left function. And notice that this is all in terms of x, this is in terms of y. So these are going to be our x values, these are going to be our y values. And that is our summary for this. That's it. I hope you guys understood it, and I will see you guys for your next video. Take care.